Hello friends, welcome again to this session. This session we will see the second article of our this chapter wave. In the last video we have seen about the particle velocity and wave velocity, what it means and how is they are differ from each other, and finally we have seen the relation between particle velocity and wave velocity. Right, now in this video we will see the differential equation of wave motion. That means what? Whenever we are talking about the motion, we must yes, we know that there is a motion, particle is performing some simple harmonic motion or a wave is propagating in forward direction, but how to represent this equation, or how to represent this motion in terms of equation, that is important. Because I told in the very first video also, whenever we have to say something in the physics, then you should have some mathematical backup for this. So we can say yes, we cannot only say about the motion, we must have some mathematical proofs to show that motion is exist. Okay, so in that way we can represent our wave motion in the form of a differential equation. Okay, so final conclusion will be that only, thus this equation will be for the wave motion. So we will start this article. So for that, now in the last lecture we know that how to represent the displacement of particle when it performs the simple harmonic motion. That is what we have written here. The equation 1, we know that the simple harmonic wave particle displacement equation or displacement x is what? Y is equal to means the wave is taking displacement along, or the wave is displacing or moving along x axis, but the particle is taking the displacement along y direction. That's why this displacement is represented by equation 1, and that is y is equal to a sine 2 pi by lambda Vt minus x. Right, in the last video also we have seen this. So this is what the general displacement equation where the particle is performing simple harmonic motion, where a is the amplitude and v is the velocity of wave. This is important. This is what? Velocity of wave, not about particle, because particle velocity is different and wave velocity is different, we have seen in the last video. So where what a is what? Amplitude, and v is the wave velocity. Okay, so and that equation 1 is the displacement of whose? The displacement of particle, not of wave. Now if I know the displacement of particle, that is in equation 1, and I want to calculate the velocity for that particle, what should I do? I should just differentiate that displacement with respect to time. Yes, and that is what we are doing in the next step, differentiating the wave equation, that is equation 1, with respect to t and keeping x constant. Here it is what? Keeping x constant. That means we do not want to differentiate x, we want to differentiate whatever may be displacement of particle with respect to time, and in that way or on that time we are keeping x as a constant. So if I want to differentiate this equation with respect to time, so left hand side will be dy by dt. Differentiate means we have to take the derivative with respect to time. So dy by dt, left hand side. Right hand side will keep a constant. First of all, yes, one step is, you can increase here one step, a is constant. Derivative of this sine, derivative of sine with respect to t, because t factor is here. Okay, x is constant but t factor is present, even though x is constant but t is here. So we have to differentiate first of all whole thing, means derivative of sine theta is cos theta, we know that. So that will be appearing here, derivative sine derivative cos, as it is theta. Here theta is what? 2 pi by lambda Vt minus x. This whole is the theta, right? Not only 2 pi by lambda, or not only Vt minus x, or not only t, this whole thing is what? Your theta, 2 pi by lambda into Vt minus x. So a is constant here, we have kept a here. Then derivative of sine is cos, so that is cos 2 pi by lambda Vt minus x. Okay, and again by the chain rule we have to take the derivative of this theta, because this theta is again a function of t. Right, now if we take the derivative of this theta with respect to time, in that 2 pi by lambda is constant, it does not have any dependence upon time. So 2 pi by lambda, here we have written 2 pi by lambda as it is. This previously a is already constant, and now if we take the derivative of this particular bracket Vt minus x with respect to time, we are taking derivative with respect to time. So here x is constant, that's why derivative will be 0, means minus 0, it does not have to written here. And then finally the derivative of this Vt. So derivative of Vt with respect to t, V is constant and the derivative of t with respect to t is 1, that's why here V is appearing. Okay, so this 2 pi by lambda and V remains constant and derivative of t is t and x derivative will be 0 because we are taking derivative with respect to time. Okay, you might have the question, no sir, x derivative is 1, but x's derivative is 1 with respect to x, we are taking here derivative with respect to t, that's why the derivative or with respect to t, x is constant we have considered here and that's why its derivative will be 0. So finally we can rewrite this equation, you can increase one more step here. Okay, so finally I have written here the final equation, dy by dt, left hand side dy by dt is equal to, now I am writing little bit precise way, in a precise way, 2 pi by lambda, 2 pi by v, sorry 2 pi v by lambda, a constant, and derivative of this sign we have taken already, that is cos 2 pi by lambda vt minus x, and we name this as equation number 2. Okay, I hope up to this you do not have any problem. So simple here what we have considered, simple one our wave equation, moreover the displacement equation, and to find the velocity, why we are differentiating, because we want velocity, this is what v, yes that v is wave velocity, but we have to talk about the particles motion, therefore we want particle velocity, and to find particle velocity we have differentiated the particle displacement, this is particle displacement, it's a derivative with respect to time, and this dy by dt is nothing but your particle velocity, equation number 2. Now let's go to the second slide, again I have taken the equation 2 here as it is, dy by dt 2 pi v by lambda a cos 2 pi by lambda vt minus x. Now this is what, now velocity of particle. One step ahead I want to go and want to find the acceleration of that particle which is performing simple harmonic motion. So this is velocity, and if we want acceleration, what should we do? Yes, acceleration is rate of change of velocity with respect to time, that means this is velocity, and once more rate of change of time or rate of change of velocity with respect to time means we have to differentiate again velocity with respect to time, and then it will be acceleration. Okay, now to differentiate, to get the acceleration, differentiate again equation 2 with respect to t, and here also we have to keep x as a constant. Okay, now so left hand side to this side dy by dt, it's a derivative d by dt of dy by dt, that means we can directly write d2y by dt square. Okay, it is second derivative because dy by dt is the first derivative, and one more time we are differentiating that term with respect to time, that's why it is d2 by d2y by dt square, that is second derivative of displacement, and second derivative of displacement is nothing but acceleration. Okay, left hand side. Okay, now come to the right hand side, equation 2 right hand side, 2 pi v by lambda is constant, write in your notebook 2 pi v by lambda, it is constant. Okay, a is constant, and now focus on this cos derivative, derivative of cos is minus sin theta, that's why here it is minus. Okay, and sin 2 pi by lambda vt minus x, that will be our, or that is our total theta 2 pi by lambda vt minus x. Okay, now again by the chain rule we have to take the derivative of this particular theta 2 pi by lambda vt minus x, because t term is present in the theta. Again if we take its derivative, then again here 2 pi by lambda is constant. Okay, this x is constant, so this constant is in multiplication, that's why we have to keep this aside, and here this constant is in addition or subtraction, that's why its value will be 0, and again derivative of this vt will be v, that means 2 pi v by lambda, one more time it will come, right? Already here it is 2 pi v, sorry, already here it is 2 pi v by lambda, here already here 2 pi v by lambda, and from the chain rule one more time we have taken the derivative, that's why here from here also we will get the same term 2 pi v by lambda, and that's why 2 into 2 4, pi into pi square, v into v square, and lambda into lambda square, this a is already here constant. Okay, and why this minus sign is here? Because derivative of cos sign is minus sign, right? And this is equation number 3, and that represents the acceleration of particle along y direction. Okay. Now keep this aside. Let us talk about the compression. Let us talk about the compression. Why the compression? Because when a wave is traveling into the medium, when particles are taking simple harmonic motion and wave is traveling into any medium, the medium experiences either compression or rarefaction. Yes, we know this is in case of wave, right? So what medium or the particle in the medium performs, or particle in the medium experiences either compression or rarefaction. So we have to see what exactly the compression and how to find the compression. So compression means, yes, these are the particles of the medium and wave is traveling. Let us consider the wave is traveling into this. So due to this wave motion, either this particle compress or rarefacts, right? So how to find that compression? This is what the compression. And this compression you can simply find if you know the displacement of particle which is performing simple harmonic motion. Differentiate that displacement along, or differentiate that displacement with respect to x. That means dy by dt is particle velocity. So similarly dy by dx will give you the compression. Here was our first equation. Okay, so what I am writing here, differentiating equation 1, this is what our equation 1, differentiating equation 1, that equation only we have written here. So differentiating equation 1 now with respect to x, not with respect to time derivative we have already taken. Okay, so if we differentiate that equation 1 with respect to x, and in this case keep the t constant, earlier we kept x constant, but now here keep the t constant and differentiate with respect to x. So if we take its derivative with respect to x, again left hand side dy by dx, because already it was y, and derivative of y with respect to x, that is dy by dx. Okay, right hand side it is already what, a sine 2 pi by lambda vt minus x. This is what the equation, a as it is, yes, a we have kept here, right? Now the derivative of cos is sine, so it is sine, already it was sine, so derivative of sine is cos 2 pi by lambda vt minus x, we have written here. Again we have to take the derivative by chain rule of this inner theta. So again in that 2 pi by lambda is constant, keep aside, here we have kept already. And now see this v is in multiplication with t, but we know that, or we have kept here t constant, because we are taking derivative with respect to x, and therefore the derivative of vt with respect to x will be 0, right? And this minus x, derivative of minus x with respect to x is minus 1, or we can say minus sign as it is here, and derivative of x with respect to x will be 1, and therefore finally what we get, minus 2 pi a by lambda cos 2 pi by lambda vt minus x, right? Equation number 4. Very simple, these derivatives not so complicated, but I have ignored one step, right? You can elaborate yourself, and if you have any doubt you can post in the comment box. Any doubt regarding these videos and you can post in comment box, right? Now next, so what we get, compression. How we found the compression? We found the compression by differentiating equation 1, that is displacement, with respect to x, and this is equation number 4. Okay, now let's go to the next slide. Equation 4, again we have written here, dy by dx minus 2 pi equal to minus 2 pi a by lambda cos 2 pi by lambda vt minus x. This theta remains same, right? Now again we have to differentiate this compression one more time. So that is equation 4. So differentiate again with respect to x, we get the rate of change of compression. Now see, if I have something and I want to find its rate, how it is changing with respect to something. So what I am taking, I am taking derivative, right? If I want to check the particular variable, let us consider a is a variable, and I want to check this variable how it is changing with respect to x. So what I am taking dA by dx. Okay, or we can say yes, how to change, how to check how the velocity or the displacement is changing. So, dy by dt same is here. So, we have to find the rate of change of compression. This is compression now, got it. Dy by dx is compression, equation 4 is compression, and we want to find how this compression is changing. That means we must take one more time the derivative of that compression with respect to x. So, yes, left hand side dy by dt dx was here and its derivative with respect to x, that is why d2y by dx square. Again this side we have to differentiate with respect to x. Okay. So, slowly we can say minus 2 pi a by lambda, we will keep this minus 2 pi a by lambda as it is. Okay, write in your notebook. Then derivative of cosine is minus sign, derivative of cosine is minus sign. So, this minus sign 2 pi by lambda Vt minus x, and again this derivative of this inner theta. So, this theta is 2 pi by lambda Vt minus x, but t is constant because we are taking derivative with respect to x. So, that is why here again it is derivative of x is 1 with respect to x, and this negative sign. So, minus 2 pi by lambda, minus 2 pi by lambda. Here again already it was minus 2 pi by lambda, here it was already minus 2 pi by lambda, and again from this double derivative we are getting minus 2 pi by lambda. So, minus plus, right, but you can say sir here again it is negative because the derivative of cos is minus, that is why 3 times minus here, from here, minus from this inner derivative, and minus from derivative of cos is minus sign. So, 3 times minus into minus, that means it is minus, and therefore, this equation 5 is also negative. And 2 pi by lambda, already here it was 2 pi by lambda, and from this again 2 pi by lambda. So, 2 into 2 4 pi into pi square, lambda in the derivative, lambda into lambda square, right, and a was already there. So, a as it is here, by mistake the a comes twice, a and a. Okay. So, only write one a, right, because a was already constant, here by mistake it should not be there, a. Okay, keep that in mind. So, this is equation 5. So, that equation 5 gives you the rate of change of compression, right. Now, look at the equation 2 and 4. Look at the equation 2 and 4. What is equation 2? dy by dt is equal to 2 pi v by lambda a cos 2 pi by lambda Vt minus x, equation 2. And what is equation 4? dy by dx. So, here dy by dt, but what is dy by dx here? Minus 2 pi by lambda a cos 2 pi by lambda Vt minus x. Okay, that means if we keep that v here, if we keep that v aside, and 2 pi by lambda a cos 2 pi by lambda Vt minus x, that is nothing what? That is nothing but dy by dx, and moreover minus dy by dx. So, using equation 2 and 4 you can get this dy by dt, or in simple words we can say substituting equation 4 in equation 2. Okay, in simple language what we say, substituting or putting equation 4 in equation 2. What is equation 4? dy by dx. What is equation 2? dy by dt is equal to, now if we keep this v aside, the remaining is dy by dx from equation 4, and here it was negative sign, therefore the negative, keep v aside. So, from equation 2 and 4 finally what we get, dy by dt is equal to minus v dy by dx, dy by dt is equal to minus v dy by dx, that is equation number 6. Now, similarly from equation 3 and 5, now let us go to the equation 3. Yes, this is equation 3, d2y by dt square, that is acceleration. And what is equation 5? That is rate of change of compression. Again here we can say putting equation 5 in equation 3. Either you can say from equation 3 and 5, or we can say in simple language substituting or putting equation 5 in equation 3. So, equation 5 is this much, d2y by dx square, and this equation 3 d2y by dt square. Again here remaining thing will be d2y by dt square except v square, except this v square. So, keep that v square aside, and remaining will be d2y by dx square. Minus sign is here also and minus sign is here, that is why that minus minus becomes plus. Therefore, equation 7 is d2y by dt square is equal to v square d2y by dx square. Okay. Now, what we get is equation 6 dy by dt is equal to minus v dy by dx, and equation 7 is d2y by dt square is equal to v square d2y by dx square. The equation 7 is differential equation of wave motion. This equation 7 is nothing but the differential equation of wave motion, where d2y by dt square is acceleration, v square is what? Which velocity? Wave velocity. Sorry, v is a wave velocity, its square, v square, and d2y by dx square is what? d2y by dx square is the rate of change of compression. Rate of change of compression. So, this particular equation number 7 is known as differential equation of wave motion. We will go one step ahead, and yes, the general differential equation, generally how to write the differential equation of wave motion, generally we write like this. For any kind of motion, d2y by dt square is equal to some constant k into d2y by dx square. This is what the general notation, and this is what we get for this our simple harmonic motion. And if we compare these two equations, equations 7 and 8, or if we use equation 7 and 8 combinedly, so what we get? Okay, d2y by dt square, here left hand side d2y by dt square, equation 7, and this also d2y by dt square. If we equate them, then finally what we get? V square is v square into d2y by dx square equal to k into d2y by dx square. So, d2y by dx square get cancelled on both sides, and what we get is k is equal to v square, right, using equation 7 and 8. And finally, we can write v is equal to, if we take the square root on both sides, so v is equal to under root k. So, by thus knowing the value of k, we can find the wave velocity. What is v? V is wave velocity, and that k is known as, if we are talking about a box which is attached to spring, and the spring or that box is taking simple harmonic motion, then that k is known as spring constant. Okay. So, it varies according to the system. So, basically that k, if we are talking about a box is attached to the spring, and we have displayed that box by the amount x, and that box is performing simple harmonic motion, then that k is also known as spring constant, right. So, simply what we get in this particular lecture is how to write wave motion in the form of differential equation, and finally how to get our wave velocity by using k. So, v is equal to under root k, and basically this equation 7 is only our differential equation for wave motion. So, I hope you got whatever I have told you in this particular video, and if still you have any doubt, any problem, you can post it in the comment box. Thank you. We will meet in the next lecture. Thank you.